Hello, everyone, and welcome to this today KEMA Labs webinar, High Voltage Switchgear, the Road Towards SF6 Alternatives. Well, I am Antonio Boccuni, member of the marketing team here at KEMA Labs, and I'm incredibly excited to introduce this awesome event today. Well, this is not the typical, not only the typical event in which talk about technical topics. Of course it is. It will be introduced quite deeply by our dream team of presenters. But this is also the history of an entire industry segment, the switchgear one, who is willing to move from a well-established technology, the SF6 insulation, towards a new alternative. Well, but what's the trigger factor behind this remarkable change? What's the pushing factor to move and get out and get outside, let's say, of the comfort zone of the SF6? Let's move to the next slide. And let's say, uh, so the SF6 is, when we will see this in the presentation, is a man-made gas that is one of the most potent in terms of greenhouse gas emissions, and one of the one which has the highest global warming potential. Well, and this is one of also the most adopted inside the high voltage switchgear installed base. So in a moment in which the world is facing the impact of the climate changes, these cannot be definitely the direction to follow. Some impressive numbers in the present slide give us the idea of what is already happening. It's not part of the imagination of a movie anymore, it's reality. A quarter of the population is at risk of flooding. 1.5 degrees increase in the temperature and the global warming temperature after the Industrial Revolution. So this is something which is already happening, but the energy sector is reacting on it. KEMA Labs is positioned on the front line together with the energy stakeholders to support them in the enablement of the change towards a greener and resilient grid. And let's say we have touched, like KEMA Labs, and supported our customer in several services, in several changes for this. Let me take the example of the natural esters that are going to replace step by step and more the mineral oils. We had an interesting webinar on this topic that I, let's say, suggest you to check out in our website. It is the webinar that we already had. The HVDC sector that is investing with infrastructures to convey renewable energy towards the main consumption centers. Also the test on alternative gas, which we are going to explore today. Test on energy storage systems, which are one of the most important ring of the value chain of the entire renewable energy segment. Well, KEMA Labs is on top on this, is a partner of several customers and is supporting them to not only test their product, but to market them in the most reliable way possible. KEMA Labs is the world leader for independent testing, inspection, and certification. 1,000 highly experienced professionals which are divided in 7 industrial facilities around the globe that can take advantage of more than 350 years of legacy experience, serving over 4,000 global customers every year. That's incredible, incredible numbers. And the main area of business which KEMA Labs is taking care of for their customers is in the testing laboratory segment, the on-site services, the inspections and product certification, and the new focus on emerging technologies with our digital labs. An incredible and awesome set of skills, facilities and competencies every day serving our clients, but also sharing and stimulating knowledge exchange in events like this one, where we have a dream team of presenters that I'm going to introduce now. Well, we have some of them we already know from past events. I suggest you to check out another webinar of the series, the HVDC webinar, the HVDC switchgear webinar, which you can check out in our website, where René, Peter, Paul, Smeets already presented that webinar, and today, like innovation specialist and convener on the SIGRE working group for the SF6 free switchgear, is here to talk about the topic together with John Owens, which is the lead research specialist at 3M United States. Well, we have also the point of view of the manufacturer of the alternative gas, Nendan Dubelda, which is our moderator, our innovation engineer at KEMA Labs, and responsible for the development on test methods and design of test circuit for HVDC switchgear. Well, I remember you that the material presenter will be available online in our website after the event, and you will, after the event, get the link to the recorded session to check out the session even after. So now, just concentrate, fasten your seatbelt, and enjoy the journey with our speakers. And remember to deliver your question during the Q&A session that Nadu will moderate. Now, without further hesitation, let me hand over the speech to René. Are you ready, René?
Yes, I think so. I am ready for starting. Thank you, Antonio. We are seeing indeed that SF6 alternative topic is attracting a lot of attention these days. And that I saw the first question already because a lot of questions are being asked. The title of the presentation today is High Voltage Switchgear. The question was, will it include medium voltage switchgear as well? And the answer is yes, we will include medium voltage switchgear as well. Well, we are going down a road. Let's travel down this winding road and see how to contribute to the green future. This road is crowded. When we ran the SIGRE workshop a few weeks ago from 3 study committees, this was the best visited SIGRE event apart from the opening session. And with 600 plus registrations for this get together now, the interest in SF6 alternatives is again huge. But first, a few words on the content of the webinar. So first, we will have a very brief introduction. Then we will say a few words on switchgear technology, and we will devote both attention to the gas-based and the vacuum-based type of switchgear. Then we will speak about the use of the media, of the gas, and the products developed. Then we will hand over the screen and the words to John, because John is giving us some important messages on the health, safety, and environment aspects of the FD gases. We will come back then with a short quiz in which we would like to give you the possibility to test your knowledge about the matter. We will then go on to the specific features of SF6 gases in switchgear. We will conclude with saying something about what is the roadmap and what is the future about application of these gases. And then we will, of course, say a few words on testing and about the international activities. And then we will give the word to you. But please, if you have any question, don't hesitate to post them on the chat, because we will try to answer as much as possible questions as we can do. So first, speaking again about SF6, as Antonio mentioned already, SF6 is the strongest greenhouse gas. The GWP of 23,500 is well known, but it's recently, a few weeks ago, it's revised by the IPCC to 25,200, so even more. Well, this implies that 1 kilogram of SF6 roughly means circling the world 5 times with a gasoline car. The global impact of SF6 emission is estimated at several tenths of 8% of the global 40 billion ton of emission of CO2. The electrical industry emission in the EU is around 100 ton of SF6 gas per year. And it's clear that EU is working on a regulation of F-gas, and taxation will be more common than it is already now. Most large TSOs have made roadmaps to reduce the SF6. One case is shown here. National Grid Company of UK will eliminate the SF6 from all its assets by 2050 and stop procurement of its extra high voltage SF6 switchgear by 2024. The state of California in the US is embarking on a phase-out plan aiming at switchgear with a GWP at 1 at most. By 2031, all high voltage switchgear shall comply. Japan sets its cards on a stringent SF6 reduction. A remarkable 0.1 emission per year has been achieved, which is 5 times lower than the standards in IEC. Oh, sorry. EU is funding development of 420 kV SF6 free circuit breakers, and in the meantime, SF6 pilots are going on, though many are with reduced stresses still. The national Korean utility KEPCO is sponsoring the development of 170 kV GIS, one track based on synthetic gas, one on vacuum plus air. And it is these 2 tracks that we will try to follow in this talk. So let's have a look at what the importance of gas in gas circuit breaker is. Well, we see 3 different technology of gas circuit breakers, live tank breakers, dead tank breakers, and GIS circuit breakers. Well, this is not only, of course, for gas breakers, but also the vacuum breakers have an outside appearance which is similar to that. Well, we can have a look in the key part of these circuit breakers. The arcing chamber of these gas breakers, they all look similar to this. Well, first of all, they are of course filled with gas. Gas is one of the important features of the device. Then what is quite important, some contacts are involved, and we have 2 types of contacts in gas circuit breakers. The main contacts serve to be sure that the normal conducting function of the breaker is with low losses, whereas the arcing contacts have to deal with the tremendous heat of the arc. Well, then, of course, quite important, and we will also come back to that, it's the nozzle of the device, which has the function to let the extinction gas flow around the arc. Well, I will try to show now a working condition of this circuit breaker. So you see in the animation now how the gas during the interruption process is compressed, and as soon as the arc comes and when the nozzle is free, there is a high pressure of gas is flowing around the arc to cool the arc and to get rid of the media of the hot plasma which is still inside. Well, this is one type of circuit breaker. The other type we will see now, it is the vacuum circuit breaker. Well, the vacuum breaker, we know, of course, already a long time because it's the workhorse of medium voltage. And one of the key points, one of the attractive sides of vacuum breaker is that its contact system is very simple. Well, I will again show an animation on how a current interruption in such a vacuum interrupter looks like. So a single set of contact is involved here, and this single contact set has to be sure that it's conducting current in the closed state. It has to interrupt the current, including fault currents to the highest level, and it, of course, it has to insulate as well. Well, here you can see an enlargement on what the difference of contact system of the 2 types of circuit breakers is. So you see the single contact set of the vacuum breaker, and below you see the main contacts and the arcing contacts of the gas circuit breaker. Well, some features of vacuum breakers is that the traditional design of the high voltage type of vacuum breakers have SF6 insulation, and they are in wide use in Japan. Details can be found in Seagray Technical Brochure 581. But since 2010, also compressed air is becoming in use as outside insulation of the vacuum bottles that you can see here. Well, having compressed air means you need a higher pressure to deal with the dielectric requirements, but it also enables a very low temperature application. Well, these days, over 1,800 installations have been are going to be commissioned, most in the United States and in the range of 72.5 kV. Well, here you see a picture of a modern 145 kV GIS. Well, let's go over to the gases now. So the pillars of switching technology are insulation, interruption, rated voltage, and technology. Well, now a new one jumps in, which is the GWP, because that is quite becoming more and more important these days. Well, first, we all know SF6. SF6 is Mr. Do It All. It is applied from medium to ultra high levels of voltage up to 1200 kV and is able to deal with fault current of 300 kA and more. It is also available in all technologies. So it's live tank, dead tank, GIS. Well, its bad phase, of course, is its GWP, and it is really only because of this that many wish to say farewell to SF6. Well, then again, the oldest alternative, which with only natural origin gases around, most common is switching in a vacuum environment and insulation with compressed air. Replacement of SF6 by natural origin gas is a natural development step because high voltage vacuum SF6 insulated switchgear is in use since 20 years. For very cold locations, O2, CO2 live tank switchgear has been developed some 10 years ago as well. Also in this live tank application case, the natural origin gas break and insulate. Well, as you can see, new gas insulated busbar, gas insulated lines, GIB, GIL developments for 420 kV are announced and use technical air insulation. Well, then the second group of alternatives based on synthetic F gases, the fluoronitriles and fluoroketones. The latter one, C5FK, we call it, come in use these days in this distribution switchgear for load current interruption and insulation. High voltage insulation in 420 kV projects is still reported with C5FK mixtures. Note that C5FK mixtures have the lowest GWP of the synthetic ones. Most new synthetic gas products these days are with fluoronitriles, C4FN. As you can see, it is applied in a number of different mixtures. Regarding GWP, the reduction compared to SF6 is still tremendous, but not as much as the natural origin gases or the mixtures based on C5FK. Well, almost all of the mixtures include oxygen for reduction of soot by the arc and the reduction of carbon monoxide. Only very recent products, one recent product leaves the oxygen out completely. Please note that the amount of the synthetic gas is low, below 10%. Thus, it is amazing that these SF gases have such a strong impact. The bulk gas is CO2, though also N2 as bulk is reported for insulation. As you see, insulation by SF6-free gases is far more easy than interruption, since GIL projects up to 420 kV are running or are planned with all the gases. Fault current interruption is limited now to 140, 170 kV. Well, Then let's have a look at the medium voltage distribution switchgear. Looking at this chart, the vast majority is with vacuum interrupters. Some designs are not new, since some companies have banned SF6 already long time ago. Combining atmospheric dry air with field control shields and some solid makes it possible to reduce the size of 24 kV ring main units to that of SF6 insulated ones. In distribution, C5FK is used here along with C4FN. The reason is the lower filling pressure compared to HV. This enables relatively high F-gas content while still keeping an acceptably low operation temperature. As we will see soon, low operation temperature, high F-gas content, and high pressure cannot be combined. In some products, arc interruption is taken care by one of the new F-gases. These are the load break switching devices. Unlike in transmission applications, all circuit breakers in distribution use vacuum for fault current breaking. Please note that the overview is not complete and just illustrates the large variety of products. A more complete overview can be found in the upcoming technical brochure of switchgear Working Group A341. Let's now jump over to some products in the high voltage field from 72.5 to 170 kV. Note the different technologies here as well. Well, first, in the green square, there is one group of products that use the alternative gases for interruption and insulation, as all SF6 switchgear does. Almost all alternative gas breakers now use C4FN mixed with CO2 and O2, while the C5FK option for high voltage seems to be abandoned now. Nevertheless, there is not a general accepted mixture composition. A number of different mixture is applied still, depending on manufacturers, but also within a single manufacturer, we see different mixture compositions. Note that there is also a product, a live tank breaker, which uses only CO2, O2 for functions, insulation, and braking. Future CO2, O2 GIS products are announced. The absence of F-gas and enables, for this case, a very low temperature application, but also needs higher pressure to cope with the dielectric requirements. The second group now, in the blue square, uses vacuum interrupters for interruption and different types of compressed natural gases, which can be dry air, synthetic air, or technical air, and even CO2 for insulation. Regarding ratings, the two technologies have been claimed to pass tests are at the same level, which are in the 145, 170 kV, 50 Ka range. An interesting development is the technology sharing between different companies. The cases here are LSIS with GE since 2016. You can see that in the upper left one, the patent sharing between GE and Hitachi ABB, which is effective since Earth Day in 2021. Siemens and Ilgin some years ago, but also Siemens with Mitsubishi and Meiden with Toshiba. Having heard of a large variety of products, most very new, it's time to say more on the new low GWP synthetic gases. Health, environment, and safety aspects are always discussed in application of new synthetic compounds. Therefore, we have invited John Owens of 3M, which is the manufacturers of the pure substance, to highlight this aspects. John, may I give the words and the frame to you?
Yes, thank you, Renee. So as Renee said, I'm John Owens from 3M, and I'll spend the next several minutes providing a few details on the fluorinated SF6 alternative gases that he described are currently being installed in electric power applications. So there's certainly been an interest from the industry in moving away from SF6 for quite some time, but it's taken literally decades of research to identify suitable alternatives. Once you screen many of the possible candidates for the key requirements, several which are shown here, the list of viable options really starts to quickly narrow. So when you try to make a combination of both the performance, the environmental, and the safety properties that are required to be a viable alternative to SF6, it's really difficult, as Renee was mentioning, to combine that into any one molecule. As a process of this selection and evaluation, two materials showed really the best balance of properties, and they're shown here at the end of the selection process. One is as Renee described, a C4FN. It's a fluorinated nitrile. Commercially, it's known as Novec 4710 insulating gas. So C4 fluorinitrile, and throughout we'll just refer to it as C4FN for short. And the second compound is the fluoroketone Renee mentioned. It's a 5-carbon fully fluorinated ketone. Again, the commercial name in this case being 3M Novec 5110 insulating gas, and we'll refer to it as C5FK. So one of the ways to develop a material that would have high enough insulation and interaction capability that Renee was describing is to design a compound that has a large electron absorption capacity. This can be visualized as shown here with an illustration of the molecular positive surface area from calculations that were done with quantum mechanics calculations. So here we compare the two alternatives Renee mentioned, the C4FN and the C5FK, compared to SF6, and you can quickly see that these are significantly larger positive surface areas, which means that it actually will have a higher electron capture capability and results in higher dielectric breakdown voltages on a molecule per molecule basis relative to SF6. But one thing to recognize is that there is a bit of a trade-off here because we've made larger molecules in order to get that electrical performance. These materials have a lower vapor pressure. They're not as volatile as SF6. So as Renee mentioned, these materials are often best used in dilute gas mixtures in order to be able to function over the typical ambient temperature range that would be required in most electric power applications. So there's a number of ways that those gas mixtures can be generated. Obviously, this is a little bit different than using pure SF6, which just comes out of a single cylinder. In this case, you could pre-mix the gases. So you provide the exact gas mixture that Renee was describing would go into one of those applications. It's a simple process. It's going to function much like using pure SF6 from a cylinder. However, it's going to require a lot more material or more cylinders to fill a large piece of equipment. This is probably the simplest process, but that larger cylinder does complicate things because you only have a limited amount of gas that you could put into a cylinder and be certain that there'll be no condensation ever prior to using that material that could disrupt the mix ratio. An alternative to that is you could also pre-mix the gas, but allow some of it to be liquefied intentionally. So this would greatly reduce the number of cylinders because now you're able to put a lot more material into a given cylinder. But the requirement would be that this cylinder would have to be heated in order to make certain that you're getting the correct mixing ratio that was intended to go into the equipment. And then finally, you could mix the materials on demand. So basically, you'd have to handle individual cylinders of each component. So as Renee described, that could be 2 or 3 components in a mixture. So it has that complication of individual compounds being managed and handled, and you'd have to have the equipment that would do the proper mixing ratio. And in reality, all 3 of these types of methods are already being used and have been used for the type of equipment that Renee described that's already operating on the grid. So what's the impact of using those kind of gas mixtures then in gas sensitive equipment? Well, this table shows an example of some of the kinds of gases that are used in the equipment Renee described. Matter of fact, I think Renee has seen this kind of mixtures come through the KEMA Labs for testing and qualification. In the case of the fluoroketone-based gas mixture, regardless of what the concentration or mix ratio is, you're able to achieve really the intended goal of using an SF6 alternative, which is essentially eliminating greenhouse gas emissions from the application. The insulin gas itself has greater than a 99.9% reduction in greenhouse gas emissions compared to SF6. In the case of the C4 nitrile, it's nearly that high, even though the GWP is not less than 1. Over the 40-year operating life of a piece of equipment, for example, it would reduce the greenhouse gas emissions by 99.5%. And in fact, if you carried out that calculation over the 100-year time horizon that is used to calculate the GWP, it too would show a greater than 99.9% reduction in greenhouse gas emissions when compared to SF6. So as Renee mentioned, another important consideration for any SF6 alternative technology is the health and safety aspects for using it in gas insulated equipment. So it's important to recognize that before any chemical can be used on a commercial scale, it's subject to a number of regulations that require a wide range of toxicological tests to be completed in order to assess any potential hazards, evaluate what the potential exposures could be to that material, and then ultimately determine if it can be used safely in the intended application. So in Europe, for example, these policies fall under what's called REACH. It's a chemical registration process that has a number of defined testing requirements, such as the ones that are shown on the right. For example, in the US, that falls under TSCA. And it's a cumulative body of knowledge that has to be developed to determine what are the potential hazards and how would this material and can it be used safely. So the testing is often dependent on whether or not what information is already known. So it's not just a box checking exercise. It is determined, to conserve animal studies to be based upon the cumulative base of knowledge for that material. And the authorities in the end ultimately have the ability to restrict the material or literally outright ban its use if they deem that they wouldn't be able to accurately manage the risks that material would pose in an application. So both the C4F and the C5FK have completed a wide range of tests and there's regulatory reviews, and they're registered on the various chemical inventories as shown here. So again, including REACH in Europe. As a result of those tests, the materials were found to be low in acute inhalation toxicity and repeated dose inhalation toxicity, and they end up being labeled in some of the lowest hazard categories under GHS, the globally harmonized system for the classification and labeling of chemicals. And then 3M's medical department sets occupational exposure limits for those materials to be protective of worker health. So again, based on that full range of toxicity tests, the medical department set the occupational exposure limit, or the OEL, for the C4 nitrile, the Nova 4710 gas, at 65 parts per million. And in the case of the C5 ketone, Nova 5110 gas, at 225 parts per million. And the table below shows, just for comparison purposes, how does that compare relevant to other materials that you might have more familiarity with? So in the case of C4 nitrile, the 65 ppm exposure limit is compared to ammonia or acetic acid, which is the active ingredient in vinegar. C5 ketone compared to like rubbing alcohol or acetone, which would be like nail polish remover, that type of material. So it's in the range of materials that people already deal with today, in their daily lives. But probably more importantly, how does that compare to what you would expect in a switchgear application? So the graphs on the right, for example, show measurements that were made on SF6 over the course of a year at indoor substations, and shows under varying concentrations of SF6 that could be found at the time of year and even during maintenance. Actually, all are well below 1 part per million. And then compares in the lower right here, how does that compare relative to these occupational exposure limits that were set that have been determined to be the safe limit that a worker could be exposed to 8 hours a day, 5 days a week, 52 weeks a year throughout their entire working life. And you can see there's actually a very wide margin of safety between where the expected exposures could be from a typical gas insulated equipment installation and what's deemed to be a safe level for workers. So those comparisons were for newly mixed gases, as just first installed into equipment, and what's intended to be in there. However, it's known as Renee described that, there is going to be some decomposition that could be generated of any insulating gas when it's exposed to arcing conditions. So a number of the byproducts that could be generated from any insulating gas could be more hazardous than the originally intended insulating gas mixture. And that would pose more of a toxicity risk to anybody that could be exposed to it. So depending on the composition of the gas, you can see different materials that are degradation products that are more hazardous that could be formed. And these would vary in concentration depending upon the amount of energy that's put into the gas, so what the actual arcing conditions entail. Try to put those into perspective. If we look at where those mixtures fall, again, on that GHS, the Globally Harmonized System scale, in this case, it uses the acute inhalation toxicity classification. It's based upon the 4-hour LC50 test in animals, as that's a concentration where lethality is observed in 50% of the test animals. So whereas new SF6 is completely unclassified, once it's been arced in, you can see it moves to a lower classification level, a little bit more hazard. And so as you know, it has to be handled more carefully. When the same thing is evaluated for the SF6 alternatives, you can see the new gas mixtures are again in a non-classified area. Again, the hazard is so low as to not warrant any kind of a hazard classification. But the used gas mixtures are a little bit more hazardous. The LC50s are lower. These are from tests that were conducted either from a series of current interruption sequences or an internal arc failure condition. And it starts to get into the same range where you see used SF6. So as a result, industrial hygienists would typically advise that the handling procedures and the personal protective equipment that are used today with arced SF6 should be applied to the used alternative gas mixtures as well. And finally, there's also a question on how would these alternative gas mixtures actually be prepared and handled at a full scale for installation at utilities. Several companies, such as the ones that are shown here, have fully developed solutions, including carts for preparing and handling gas mixtures, instruments to be able to analyze those mixtures or detect leaks, and then ultimately units that could recover gases for either for disposal or potentially for reprocessing them for use at the end of the life of the equipment. So in summary, on the new alternative gases that are being installed, the Novak insulin gases, C4-nitrile, C5-ketone, they were developed specifically to have the required performance and safety properties for use as an alternative to SF6 and provide a significant and really meaningful reduction of the environmental impact. As we showed over the life of the equipment and certainly over a GWP calculation, it can be up to 99.9% reduction in the greenhouse gas emissions. The products are registered now on the chemical inventories around the world. And that's as a result of the extensive toxicological testing that's taken place that identified what potential hazards there could be and established with safe use for the materials. And as I showed, compared to expected exposures to insulating gases, there's a very wide margin of safety. And then finally, gas handling equipment has been established, not only for preparing mixtures and initially installing them, but also for recovering them at the end of life of the equipment. And I'll turn it back to Renee.
Thank you, John. I think it's now time for a quiz. Does anybody wish to announce it?
Tony.
Well, thank you, Renee. Thank you, John. It was an awesome presentation, really. I could follow, was really, really interesting. And now we have the moment for which I was personally speaking all the time, trembling at school to get some questions to test immediately the knowledge, well, we want to test your knowledge now, of course, in a funny way, in a relaxed way. You will have just to be relaxed only 90 seconds, but I hope that you will enjoy the quiz. So hands on your mobile phone or whatever is the device that you can have with the camera and scan the QR code. The countdown will start in a moment. After the quiz, during the Q&A session, at the end, I will share the main results and we will, let's say, share this funny moment. But let's say now, I think we can start the countdown. For all of you that won't be able to scan the QR, I'm going to post into the chat the link to access the quiz. Enjoy.
So please try.
I really tried to have the quiz, René, and I hope, luckily it's anonymous, but
Yes, well, it's my understanding, Antonio, that by the end of the talk, in about 15 minutes, you are going to give the results. But for the people who took
yes,
part, in the quiz, I hope when they did some examination as a student, their supervisor gave them more time. So
me too, I hope.
good. Let's continue with the real hard work then, because we want to give you some inside information on some key performances of the gas mixtures known so far. Because we know, of course, that the new synthetic mixtures, they need to perform two key functional duties: insulation and switching. Well, let's first have a look into insulation. The new and independent study regarding this aspect is done in SIGRE Working Group D167, who organized a round-robin test campaign with a large number of high-voltage labs around the world with a number of gases, and they compared these with SF6. The conditions of the test are identical, and the results are shown in the graph, which shown the observed breakdown voltage against AC and lightning impulse voltages. Well, you can see that in these graphs here. As can be seen, the breakdown voltage for the new mixtures is lower than that of SF6 at the same pressure. And this is the reason that in the new products, the pressure must be increased. Increased to at least come close to the SF6, to the dielectric performance of the SF6 gas. By the way, pure F-gas outperforms SF6, but due to the thermodynamic constraints that we are going to discuss, they cannot be used in the pure forms and need to be mixed. Well, then next, of course, in line is the current interruption. We see that in many parts during the interruption process, the new gases show different features. Well, first of all, one of the features is the voltage of the arc. Well, during the high current phase, there is some partial decomposition of C4Fn, C5K. We will come back to that point soon. Then during the arc, there is an arc voltage, so the arc energy is different in the new gases. But also speaking about the interruption itself, the interruption capability is depending on the decay of arc conductivity in the last phase of existence of the arc. Well, during the interruption process, there is a buildup of pressure inside of the chamber of the breaker. We have seen reports that there is a higher transient pressure peaks in the new gases. Speaking about the thermal recovery of the new type of gases, we see that the post-arc current, which is instrumental in the decay of the plasma after interruption, is higher, so designs need to be adapted to that, which also applies to the dielectric recovery of the breaker after the arc is gone. It is therefore of no surprise that for these non-SF6 gases, a new design of breaker is essential. There is no way of taking the SF6 gas out and putting the alternative gas in. Fault current interruption is a delicate process that is basically determined in the last few microseconds before interruption, where the remaining arc plasma needs to be removed from the switching gap. Designers have mastered this process also in the new designs, which means that if you compare the interruption of the new gases with SF6, it is stated that the capacitive switching is equivalent to SF6. The low short circuit duty, which in standardization terms are termed T1, T10, T30, require a slightly higher blow pressure compared to SF6. For the high short circuit duties, T100, the full short circuit current, They seem to be in a similar way, but the exhaust cooling system has to be adapted in a new design. Well, regarding the most critical test duty of all, the short circuit fault, the L75, the L90 performance seems to be around 20% lower than SF6. So again, new designs need to be adapted for that. Well, we need to understand a little bit on how and why of the new gases work from a thermodynamical point of view. What we see here is the phase diagram of SF6, a chart predicting at what pressure and temperature the SF6 gas condenses, so will lose its power, because only the SF6 works as a gas. Apart from current and voltage, a very important parameter of the switchgear is its minimum operational temperature. At this minimum temperature, sufficient gas, of course, must be inside to fulfill the duties of the device. Well, the drawn lines in this picture are the isocores, which are the condition of constant amount of gas, constant amount of molecules in the breaker. Well, as initial condition or nominal condition, we choose the 20 degrees 8 bar, which is a quite safe zone because there is more than enough gas inside. But we see two mechanisms of loss of gas here. Well, first is the cooling and the condensation at point B to end at the minimum condition in point C, at which more or less more and more gas will condense to end on another isocore. The second loss process is through leakage and permeation, as you can see here. Well, this happens, of course, during the entire life of a breaker and can reach the minimum functional pressure for insulation. And this is the condition D, which is the condition of a type test. Well, in this design here, the blue track is the operational lifetime cycle of this braking device here. Alternatively, a lower gas density can be chosen as the nominal condition, like point D. The advantage is a lower gas pressure, but now there is just enough gas inside, so no condensation is permitted at minimum temperature. Well, this is then the green track you see here. Well, whether to choose the blue or green track is a design choice. The blue track at higher pressure, allowing condensation, and on the safe side dielectrically, or the green track, which has a lower operating pressure, no condensation, but less margin from a dielectrical point of view. So this is again for SF6. So let us now compare the new gases with SF6. Well, here are the phase diagram. Again, this exactly the same picture. Here you see again the vapor curve of the SF6 gas, but now we have added the pure C4FN and the pure CFK lines. Well, SF6, of course, is by far the most volatile gas of the three, and it's immediately clear that pure SF6, pure F gases are unfit for the circuit breaker due to the high condensation temperatures. The trick is reducing the pressure of the F gas. The F gas can operate under a much lower partial pressure and needs a large portion of a buffer gas, CO2, at a much higher partial pressure for dielectric capability. This is why only a small fraction, a small portion of F gas can be allowed inside. And because in high voltage switchgear, the pressure needs to be higher than in medium voltage, we can see that a difference is there. Well, comparing then C5FK with C4FN, we can see that for application at lowered temperatures, C5FK is as the least volatile gas has a bigger issue, especially in high pressure, high voltage applications. This is the reason why C5FK is ultimately abandoned as circuit breaker gas in high voltage switchgear, while it can function well in the lower pressure equipment for medium voltage. By the way, the condensation curve for natural origin gases, N2, O2, and CO2, the very volatile gases, are far beyond this range here and have no issues at all with condensation at low temperatures. Well, the supreme degree, which I'm not even trying to explain, the supreme degree of complexity is in the mixture of the gases. Thermodynamics becomes very complicated in this case. There is not any longer a single boundary between the liquid and the gas. Well, the new feature now is that components of a mixture will condense one after the other. The example chosen here is the C5FK. As can be seen, this component already starts to condense before -5 degrees. And therefore, at point B, the composition has already been changed from 5% C5FK to 4.5 C5FK. Care must then be taken that the reduction of the effective C5FK, which is 10% in this case, does not reduce the dielectric capability. Low F-gas content application at lower temperature, on the one hand, it reaches lower temperatures on the one hand, but it reduces the dielectrical withstand on the other. Well, a new feature of F-gas applied as interrupting medium is that the switching arc energy consumes the gas over the life at a rate of about 0.3 to 0.5 mol per megajoule. This is new compared to SF6 that is consumed only in a very slight way. Consumption of the internal parts of the arcing chamber is of course not new, and we need to compare the new wear mechanism with the existing one. Well, here you see again the arcing chamber of a gas breaker. So due to the intense heat of the arc, there is a loss of mass of the arcing contact here, and there is also a so-called ablation, a loss of matter of the nozzle. Well, the new wear mechanism is decomposition of F-gas. Well, this is investigated, of course, and what you see here is a chart which shows the number of current interruptions. So this is showing the energy of the arc, and this is the wear during the life of a switching device. Well, with the first line shows, this line shows the ablation of the nozzle, which is reaching a limit at this point. The red line is the operation limit regarding the wear. Well, then we see the other one, the so-called arcing contact wear, is going with this black line. So it will reach the limit long after the limit of wear of the nozzle has already been reached. But the important feature here is of course, where does the F-gas reach the limit of its wear? And here we see this will depend on the volume, on the amount of F-gas which is inside of the breaker. In case a 200-liter tank, which may apply for a live tank breaker, then we see that limit is reached already at this point. So in this way, just before the end of life of the nozzle has been reached, whereas a much bigger, let's say a dead tank breaker, reaches that point only at that point in time. So we see that a small limit breaker reaches the gas wear limit faster than large ones. Well, the last slides, we would like to share some future outlook in transmission applications of SF6 alternative gases. Well, first we take a look at the technology roadmaps that various companies have in place only since the last few months. We combine here 4 major high voltage equipment suppliers in a single chart that you see at the right side here. Well, the future products are classified into 3 groups. The first one, shown here in green, is the F gases for insulation and switching. The light blue one is the natural origin gas for insulation and vacuum for interruption. And the dark blue one is the third class, which uses the natural origin gases, both switching and insulation. Well, it can be seen that all 3 technologies are available up to 145 kV right now in 2021, and 2 technologies plan to reach the 550 kV level before 2030. The F gas is planned to be the first to reach this milestone, and is also planned to reach the 420 kV GIS already next year. Well, referring to today's title, The Road to SF6 Alternatives, it's now clear that, like the way to Rome, there are many. Maybe there is convergence towards the single high voltage F gas with C4FN as the effective gas. Still, a number of alternative mixture composition are in use or proposed. And in the end, it remains uncertain when or whether the alternatives can match SF6 in pure braking power. Let's have a more concrete look at projects that are involved here. Well, the insulation capability of SF6 free gases is under demonstration right now. 420 kV GIL has been in operation a few years already with F gases mixed with CO2 or N2 as a buffer gas. Natural origin gas insulated bus ducts have been announced. A number of SF6 free 420 kV substations are in development. Well, in those cases, in the first phase, SF6 breakers will be inserted in the SF6 free GIS, whereas in the later phase, the adequate SF6 free breakers will be inserted when these become available. Looking at the interruption then, yes, it is clear that interruption without SF6 is more difficult than insulation. Several pilots are ongoing with F-gas based GIS, though in quite a few cases the rated voltage of the pilot GIS is chosen to be higher than the actual system, such as 145 kV breaker in 110 kV grid to build a margin in a first step. What remains unanswered is when and whether the alternative can match SF6 in power of interruption. Look at the graph at the right side, where the growth of the braking power in a single SF6 interrupter is shown over time. Please look, we are speaking about the interrupting power per brake here. Well, you see already by 1995, the maximum was reached 550 kV in a single gap. When roadmaps announced 420 and 550 kV circuit breaker, it remains to be seen how many braking units are needed to fulfill this task. Well, having all this information at hand, it is still not easy to decide what technology to choose. The most important factors are what to expect of taxation, even banning of SF6 gas. It's not only the GWP of the gas that counts, but the entire life in an LCA study, because lifetime losses play a role, manufacturing footprints, and so on. And what about HSE? What is the acceptance of a new synthetic compound, though this is entirely regulated and classified, as John made clear? Size matters, pressure, cost, operation, temperatures all play a role. How is the acceptance of different gases in one station, one installation? Will new SF6 alternative products come to the market? All technologies are new, but what about long-term operational issues which may not yet have been discovered in pilots that run just a few years at most? And what about scalability? To what voltage level a single brake design can come? Many brakes, more brakes per pole, always increase the size and mechanical complexity. Well, we can say a few words on how system operators are embracing the change. So let's go to an impression on how TSOs embrace the SF6-free technology. Well, these are the results I'm going to show from a small scale survey at the Seagray workshop a few weeks ago. Well, what we ask, when do you plan to install SF6-free GIS? 80% says within 5 years. When do you stop buying SF6 equipment? 74% says within the next 10 years. Is a higher price allowed for alternatives? 63% says yes, you can. Did you decide already on a certain technology? 72% says not yet. What do you think of the state of knowledge and experience? Is it enough for a wide use? 87% says not yet. What do you think is the most important decision factor to decide on new switchgear? 82% says it is reliability. So my takeaway is that there is no uncertainty about a willingness to change, but there is uncertainty on the technology readiness level of the alternatives at this stage. Well, then now jump to the last slide, because last but not least, of course, some words of testing need to be said. A few words on testing and KEMA's road into the SF6 alternatives. The new switchgear is newly designed, both the gas and the vacuum switchgear. In the case of SF6 gases, the precise composition of the SF6 mixture must be matched with the design of the breaker. So it's not straightforward, we have seen, to understand the physics and the thermodynamics of the multi-component mixture, not like a single gas. Well, some guidance of this is going to be provided in the upcoming IEC 62271-4. For quality assurance, an independent type test certificate gives at least a design-checked, a healthy birth certificate. Then it's argued in the international commissions whether the existing test duties which come from the SF6 time are still valid for the alternatives. Conflicting data is reported that state different short-circuit test duties to be the worst case. One could discuss the relevance of pre-qualification test programs, which for high voltage cables are quite common, which are focused on the lifetime endurance of alternative switchgear and looking to the impact of the gas consumptions on the dielectric capability. Well, the past 3 years, KEMA has tested switchgear with new SF6-free solutions, apart, of course, from the standard air-insulated medium voltage VCBs, from 15 manufacturer sites up to 170 kV50Ka in 3-phase synthetic test setups. Well, in last year's COVID pandemic testing continued even by remote interaction with the design teams at their homes. Almost all tests we have seen were R&D related, with all gas mixtures that are mentioned in this talk and with all short circuit and switching test duties that are in the standard. Well, this slide shows the last one. I give an overview of the international teams that are working in this field. Most of them have work in progress, that are the last ones in gray, and I'm not going to read them all. Only one is open for new members at this time. It is the bottom one. Most recently, a new CGRE working group on a gas user guide has been started. Again, with 50 members, this is a very well attended group. Please hurry if you like to join. And with that, I would like to close off and thank you for your kind attention.
Maybe you would like to make a correction in the end of the slide, Jan?
There was a remark already made on at least one mistake that was being made. We mixed up the Schneider with the Siemens switchgear. So here you see the corrected version in which the change was made. Thank you, Nado. We start the Q&A session now, but maybe we can hand over the microphone to Nadu now, who is going
Yes,
to show
guys,
us.
sorry to jump in 1 second. We have
Of course.
only 8 minutes last for our Q&A session because we enjoyed a lot the topic. We went run over time. But for all of you that cannot join and have a busy schedule, we will send the link to check out the Q&A session later. Okay.
Yeah.
Thank you very much to our lovely audience. And now let's enjoy the Q&A. Sorry, guys.
Yeah. Thank you, Antonio. Thank you, Rene. Thank you, John, for very excellent presentations. I think the audience have enjoyed as much as I did. I was quite busy collecting questions. We have over 40 questions which were asked by our active audience. I think we might not have time to go through all the questions, but we try to cover as much as possible. Of course, like Antonio said, I also posted for the audience that in case you have other schedules, of course, you are allowed to leave. And the recordings and the presentations will be shared on our website, which you will find later. Well, there was already about medium voltage question which was asked, and you already covered that, Rene. There was a question to John specifically regarding how does 3M look at recent patents granting for Novec-based gas mixture percentage rather than those connected with the designs. Don't such patents prevent or block future Novec usage by other competitors? What is 3M's approach? John, can you say a few words about this question?
Can John read the question?
Yes.
Yeah, okay. Am I unmuted?
Yes, now you're
fine.
on.
Yeah, okay. Yeah, so I can't really speak to other companies' patents, but 3M provides an implied license to use the patent that we have, for example, that covers the C4 nitrile in electric power applications. That comes with the purchase of the Novec 4710 inherently. As far as other people's patents, like I say, I can't really comment on them directly, but as Rene pointed out, there's a lot of cooperation already in the industry. So I think you can see that's already heading towards some cooperative agreements to make it certain that the technology is available to the industry.
Yeah, thank you. Well, I proceed with the remaining questions. Of course, as I say, we have quite a large number of questions. The other question was SF6 is not only applied in switchgear, that's clear. What percentage is used in the global power networks? Can you say a few words about that, Rene, maybe?
Yes, there are a number of conflicting reports on the exact number of or the approximate number of the amount of SF6 that is used in power grids. There was quite a few SF6 which was stored in Windows, but it seems that looking to the future, around 80% of the SF6 that is used is going to be emitted by power grids if there is no change. So it is still a significant portion of SF6 is released by our industry in the order of 80%.
Yeah, okay, thank you, that's clear. And regarding technical air, what gas constituent is classified as technical air?
This answer I do not know by heart. I'm not a gas specialist. We have a chapter on air in the technical brochure of our secret working group A341, but I am afraid I do not have exactly the composition of the different type of airs, because we found out there are many airs.
Okay.
But you can find this.
Okay, that's fair, yeah. For switchgear with F-gas, that the internal arc fault performance remains uncompromised. Maybe Rene or also John could say a bit about that.
Let me start to say a few words. We still think, and that thinking is shared by the manufacturers, that internal arc performance of F-gas filled devices should be no different than medium voltage switchgear filled with air. We did a number of internal arc medium voltage panel testing with F-gases filled. So the answer is it is not a difference regarding other type of insulating gases.
Okay, clear. The other question is, what is technical benefit of including oxygen in high voltage mix for C4FN versus just CO2 other gases than with C4FN? I think maybe John, you can say a few words about this. It's difficult to say which one is for Rene and which one is the.
Yeah, sure. I think Rene did address that, somewhat in his presentation. It's primarily there to help sort of suppress any soot production, because these are carbon-based materials. Chain is the backbone. And so it's really going to help try to drive the degradation product showed towards things more like CO2, for example, and maybe less of CO, which would be more hazardous. So it's really for both, safety and operational purposes.
Okay. Good.
Yes, thank you.
Yeah. The next one is the footprint of medium voltage SF6 free gas insulated as compact as medium voltage SF6 free best gas insulated switchgear?
Yes, if I can come to that point, we have at least one example of air insulated medium voltage switchgear ring main unit type, which is as compact as SF6 insulated one. So the simple answer to this point is yes, it can be.
Okay. I think there are, I'm not showing that question. There are also a lot of questions asking, can we replace SF6 with SF6 alternative gases with existing installation of SF6? Would that be possible?
No.
That's a short answer.
Yeah.
That's good. Yeah. Well, about the secret technical brochure you mentioned, I think that is clear. Members will only access it. I think non-members cannot access the technical brochures.
Well, they can, but they need to pay.
Yes, he is asking for free, so I think that is clear. Yes. What will be the procedure for refilling of switchgear in use with the gas mixtures? Will all gases have equal usage or leakage rate? Can you top up the mixture, or would a complete replacement be required? I think that's also related with what I just asked. Maybe if you shed a little bit of light there.
Yeah, maybe also John can say a few words about that. But what it was, of course, these matters, how to deal with new gases from an operational point of view, was also an important discussion in our working group.
Mhm.
It is clear, I found out that it's clear that it is possible to top up the mixture. There is no need of a complete replacement.
Yeah, okay. John, can you say a few words? Please feel free to jump in also, because as I said, the questions were not directed to specific speakers. So if you have some thoughts, I'll be glad to hear.
Sure. Yeah. In this case, the equipment manufacturers are addressing issues like this. They recognize, certain elastomeric materials that would be used as O-ring and gaskets could preferentially leak, say a smaller molecule like CO2 or O2 relative to the fluorinated materials. And so they're trying to address that. That's why they're even changing some of those components to help make certain that that is reduced. Just one other comment. I didn't get a chance to jump in there on the retrofit question. Renee is right. There's no universal replacement where you can go out and just pull out SF6 of any given piece of equipment, put it in. Part of it's this leakage issue. You want to make certain that you have the right kind of seals and gaskets. You also have to make sure the materials are fully compatible, so it'll last over the the years or decades it could be in use. But there are some situations where it's possible. University of Manchester published a paper not too long ago on this, where they looked at it. It was for a gas insulated bus, so it was for insulation purposes only. But they showed in that case, they have the potential of doing that for some equipment designs. By the time you get to a circuit breaker, or a switch where you have active arc interruptions, that's likely to be much more complicated in terms of the redesign that would be required, and it's not too likely that you'd make a replacement there.
Yeah. Good. Thank you very much for the excellent answer. Actually, I think we are well over time.
Yes. So
Yes.
we got a message from the boss that it's really time to close, and
Yeah.
I think that is.
Maybe if
Thank
I may
you.
say, Antonio, I think the more questions could be asked directly to the speakers. Maybe you can send the emails and you can get answers.
Sure.
We cannot cover all the questions.
Sure.
Absolutely. Absolutely. It will be my pleasure to take care of this separately, so we can follow up even at the end of our event, let's say. So let me share now my screen, and let's say thank you very much. Thank you very much to everyone who joined. Let's say thank you to our speakers, and especially to our guest star, John. I think you guys, together with Renee, delivered such a high value for our audience. And let's say it's a pleasure all the time to introduce and close KEMA Labs webinar. Let's say thank you very much. Thank you very much to everyone, and stay tuned for future webinars, articles, news, or interacting with us in our social media channels on LinkedIn, on Twitter with the Chasey account. We have also our LinkedIn KEMA Labs account. Stay in touch through our website. We would love to get in touch with you, to get in touch with our customers, and let's say deliver the value that you can see in our webinars, but delivering the value in, let's say, enabling the change toward a greener grid. Okay. Thank you. Thank you very much to everyone.
Thank you.
Enjoy the rest of your day.
And thank you for your patience. Thank you.
Thank you.
Bye-bye.
Bye-bye.